Okay, so first of all, of course, I would like to very much thank the organisers for inviting me to speak here. It's a great pleasure to be back at AGC2T. And while I'm still on this page, I'd like to just say a couple of things. The work I'm going to describe to you is all joint work with Nuno Freitas, who's currently a postdoctoral fellow at Warwick. He is has a Marie Curie Research Fellowship funded by the European Union. And all three of the organizations whose logos are at the bottom of the screen provide me with funding in one way or another. And I'd just like to say that I very much hope that the one in the middle will continue to be able to fund people like Nuno to come and work in Warwick and many others for many years to come. Okay, so I'm going to talk about congruences between elliptic curves and their symplectic type. And there are essentially two sort of sides to the story I'm going to tell you. One is more computational and one is a little bit more theoretical. I'm going to describe to you the project that Nuno and I started out to do was to go through all of the elliptic curves over Q in our database, which contains 2.5 million curves, to try and find all the congruents we could and say as much as possible about them, because it's something, this idea of trying to distinguish between symplectic and antisymplectic congruences, which I'll define in a minute, is something that he had been working on for some time earlier, jointly with Alain Krauss. And as we did this, we came across one or two phenomena which we weren't expecting, and we actually proved some theorems as well. So there's kind of two aspects. There's some are more computational, and some at the, towards the end are a little bit more theoretical. So that's the rough overview of the talk. I'll start out by giving a bit of background and definitions, because not everyone in the room is an expert on elliptic curves and Galois representations, although some of the people in the room definitely are. I'll mention the Frey-Mazur conjecture, where we have a little something to say, and then I'll talk more about the computational part of the project, finding all congruences, and how to determine whether they're symplectic or not. And then at the end, partly time permitting, I'll tell you some of the theoretical results we have about congruences between elliptic curves which are twists. Okay, so to start with, let's fix some notation and some ideas. Mostly I'll be talking about elliptic curves defined over a number of fields. In the computational part, it'll always be over Q, but the theoretical results don't require K to be Q, and in fact, a lot of them probably don't require anything more than to avoid certain characteristics. Very occasionally, I'll use short Weierstrass models of elliptic curves, which, as we all know, define smooth curves if the discriminant there is non-vanishing. If we look at all the K rational points, they form an abelian group. And in fact, if you replace K there by any extension field, L of K, then E of L forms an abelian group. And since we're working over number fields, it's even a finitely generated abelian group. But the part of the group that we're going to be interested in is the torsion part. And specifically, if we fix an M, then this notation, E square brackets M, or EM, is the set of all points of order M, or order dividing M. It's just the kernel of the multiplication by M map. So that's obviously then a subgroup. And we'll be looking at this mostly almost entirely for M being a prime. So as an abelian group, this is always just the product of two copies of Z modulo MZ. But of course, it has more structure than just the abelian group structure. For a start, if M is prime, it's already a vector space. But there's more structure than that, because we have Galois action. Note that the elliptic curve is defined over the field K, but here in this definition of EM, I allow points to have their coordinates in the algebraic closure. So we can take a point and apply a Galois automorphism to it and get a new point. So that's how these mod P Galois representations arise. We take GK to be the absolute Galois group of K. And so it acts on the points, because it fixes the coordinate, the coefficients of the curve. So if you apply a Galois automorphism to both the coefficients of a point P, then you get another point P on the curve. And this is not just a bijection from ek bar to itself, it's actually preserves the group structure because the group structure is given in terms of rational functions with coefficients in k itself. Okay, so each em is a gk module, and this is true for all m. So in particular, when m is prime, we have a two-dimensional vector space over fp. So this is our two-dimensional mod p Galois representation. The notation for that I'll use is rho bar EP. The bar is to kind of remind you that there's really a p-adic representation of which this is a reduction mod p, but I won't be doing anything p-adic in today's lecture. And to make things a bit more concrete, if we fix a basis of the vector space, then we can get a matrix-valued representation. So rho bar is then a representation with values in this group GL2 over FP. And that's the mod P Galois representation, which of course plays an extremely important role in many aspects of the theory of elliptic curves. Okay, but there's even more structure than that. So it's not just a vector space with a Galois module structure. It also has a symplectic structure coming from the Weil pairing. The Weil pairing on points of order P. This would also, what I'm saying here would also be valid if P was an arbitrary integer greater than 1 at least, but let's fix with a P. So the Weil pairing called EP, or E sub EP if I need to include the curve in the notation. It's an alternating bilinear pairing with values in the pth roots of unity. Now, almost all places in my talk, P is going to denote an odd prime, so please don't start making objections as to the difference between alternating and antisymmetric. P is going to be odd and it won't matter, and for P equals 2, everything I'm talking about is rather trivial anyway. So it's bilinear and alternating, so when you swap the points over, the root of unity you get gets inverted. And this respects the Galois module structure. It's Galois equivariant, so that if you take 2 points and you first apply a Galois automorphism sigma, does that? Yeah, okay. And then apply the Weil pairing. It's the same as if you apply the Weil pairing, then apply sigma to it. And of course, we know how Galois acts on roots of unity. It raises them to some power, and the power is given by the mod P cyclotomic character. Okay, so the Galois module structure and the symplectic structure are kind of intertwined like that. Okay, so for every curve E and for every prime P, we have this vector space with a symplectic structure and a Galois module structure. And that's what we're going to be interested in throughout my talk. Okay, so the kind of question we're going to be asking is, does it ever happen that you have two completely different elliptic curves, E1 and E2, which end up with the same P torsion as a Galois module?
For a given P.
For a given P, yep. So sometimes we'll be fixing a curve E and letting P vary, and sometimes P will be fixed. Mostly P will be fixed, yep, for a given P. Yeah, I mean, if it was a different P, it would kind of be a vector space over a different field, and yeah, I'm never going to compare E1 with one prime and E2 with another prime. Okay, so is it possible to have two different curves with isomorphic P torsion modules? And the answer is yes, otherwise there wouldn't be very much to say. So if this happens, then we say that E1 and E2 satisfy a mod P congruence. So saying a mod P congruence has nothing to do with whether the coefficients are congruent mod P or anything like that. It says that the mod P representations or the P torsion modules are isomorphic as Galois modules. In other words, that you have a map from one to the other, which is not only an FP linear isomorphism, but it's also GK equivariant. So in that case, we say that E1 and E2 satisfy a mod P congruence. And so that's what we're asking. Can this happen other than E1 equals E2? If it does happen, then we go a bit further, and by seeing what it does to the symplectic structure, basically there are two different things that can happen. It can either preserve it or invert it. A little bit more precisely, if you take 2 points, so these are two points of order P on E1. And if we apply the linear map, we get points on E2, and we can evaluate the Weil pairing there. Well, that will be another antisymplectic non-singular alternating pairing on E2, and so basically it must be a power of the Weil pairing on Yeah, sorry, on E1, and so it must be a power of the wave pairing on E1. So it's the wave pairing on E1 raised to some power. This exponent d phi only depends on the map phi, not on the points p and q. And the only thing that matters as far as we're concerned is whether that exponent is a square mod p, whether it's a quadratic residue. So if that is a quadratic residue, then we say that this particular mod p congruence is symplectic. And if it's a non-residue, it's antisymplectic. Niels?
So for p is 5, for instance, there's also these other types. Are you not considering them now? That's the ones that are neither symplectic or antisymplectic?
Well, according to this definition, every element of fp star is either a square or a non-square. So according to this definition, there aren't no others. I'm not just saying d phi is plus or minus 1, no. I'm just distinguishing squares and non-squares. Right. Okay. Okay. So now it is possible that between the same two curves with the same prime p, you might have both a symplectic and an antisymplectic congruence, but if that happened, then you, by composing one with the inverse of the other, you'd have an antisymplectic automorphism of E1p, and actually that can't happen in the case that E1p is an irreducible representation, because by Schur's lemma, if E1p is irreducible as a Galois module, then the only automorphism has a scalar multiplications. And you will see that if phi is just a scalar multiplication, you're multiplying both points by the same scalar, so the d is the square of that scalar. Okay. Right, so there's one situation in which it's very easy to construct congruences, which I want to kind of explain so that we can, in a sense, eliminate it, and that's when you have an isogeny. If you have an isogeny between E1 and E2, and as long as the isogeny degree is co-prime to P, then the isogeny induces a map from the P torsion on E1 to the P torsion on E2 that has all the properties we want. Assuming the isogeny is defined over K, this will be a GK invariant map. And there's a very easy criterion for the P congruences that arise this way to say that whether they are symplectic or not. They're symplectic just if that, according to the degree of the isogeny, whether it's a quadratic residue or not. And I'll prove that to you because we're supposed to always prove something in a talk, and probably this is the easiest thing. So you just do a little calculation. It's based on Weil reciprocity. So if you apply the isogeny to P and Q and then apply the Weil pairing on E2, then by Weil reciprocity tells you can kind of pick up this isogeny and put it down over here with its in its dual. So phi hat is the dual, and then phi hat times phi is multiplication by the degree, and so by linearity that gets raised into the power. So this is an example of the formula on the previous slide, and the quantity I call d phi there is just the degree of the isogeny. Okay, so if we're working with p equals 7, then 2 isogenies induce symplectic congruences, whereas 3 isogenies induce antisymplectic congruences. Okay, so now we can refine our question and say, okay, apart from isogenies, are there any other congruences? And the answer is yes, but as p gets larger, they become rarer, and it is conjectured that they die out altogether. And I'll say a bit more about that now. So that's the subject of the Frey-Mazur conjecture. So there are very slightly different forms of this. I won't go into it in great detail. So this is stated over Q. You could replace Q by a different number field if you wanted. So in its uniform version, it says that there is some constant, depending only on the field, in this case Q, such that basically the only mod P congruences between elliptic curves arrive through isogenies for P greater than that constant. Okay, so for almost all but finitely many primes, there are no mod P congruences except those furnished by isogenies. And there are various ideas as to what the correct value of this C is, but the conjecture hasn't been proved. The non-uniform version of this would fix one curve E and ask for a bound depending on E on mod P congruences between that curve and all others. And this is the uniform one where you kind of let E1 and E2 both vary. Okay, so as we'll see, over Q, mod P congruences that don't arise through isogenies exist for all primes up to 17, at least. And one theorem that we have is that if you restrict to elliptic curves of conductor less than 400,000, which is perhaps rather a pathetic thing to do because that's only a finite set of curves, right? So you could just compare each one with every other one. But our proof is slightly cleverer than that. But in this range, which is all the elliptic curves in the LMFDB database, and the elliptic curve part of which used to be called the Cremona database, but isn't any longer, in our database, there are no congruences modulo any prime greater than 17. But for all primes less than 17, there are. Less than or equal to 17, there are. And I'll say something about how we prove that a bit later on. So, as I say, there's quite a lot of history behind this Frey-Mazur conjecture, which I don't really want to go into. Some people have been known to conjecture that it actually holds with 23, because they seem to think that there is no, the world wouldn't come to an end if you found a 19 or even a 23 congruence, although nobody has found one. But somehow if you found a congruence modulo whatever the next prime after 23 is, then somehow something more serious would happen. So for the small primes p, for reasons I will come on to in a minute, for p equals 2, 3, and 5, they are really very, very common. And so we I'll ignore p less than or equal to 5 almost entirely. And then as p goes up through 7, 11, 13, 17, they get fewer in number, as I'll show you very explicitly. By the time we get to 17, there's essentially only one, and it's associated with these two curves. And if you ever get a chance to follow through this talk on the PDFs yourself, you will find that whenever I give an elliptic curve label, I haven't tried this on a Macintosh. I don't know how Macintoshes work. This document is trying to connect to. Is that okay? Yeah, okay. Anyway. Okay, so every elliptic curve has a home page, and this is the home page of this curve. And in fact, this curve even knows that it has this nice property, because right down at the bottom, it actually says, you can't read that, it's too small, but it says that this curve is mod 17 congruent to another curve. Anyway, oops. Okay, so right. So now I'll talk about how we find congruences in the database, both for individual primes p and, as suggested by the previous theorem, somehow for all primes, which clearly we didn't do one at a time. And so here's an idea of how big the database is. And of course, I would encourage you all to click on things when you find you can, because that's the link to the elliptic curve database for elliptic curves over Q at least. And we've got 2.5 million curves, and up to isogeny about 1.75 million. So one thing we don't want to do is look at curves one by, we don't want to look at all pairs of curves and say, are they congruent and modulo what? Because, 1.75 million choose 2 is too big. So we want to do something else. We only want to find congruences between non-isogenous curves, so we'll start out by picking one in every isogeny class. And we're going to start out by comparing the traces of the representation. So the traces of the representations are just the numbers AL of E that appeared in Alina's talk. And if the two curves satisfy a p-congruence, then you know that the AL of E1 and AL of E2 are going to be congruent mod p. And I put here, we're going to exclude the primes dividing p and both conductors, because, as I think Alina even said, that if you have this congruence for literally all p, then the curves must be isogenous. But this is something we can check. So if you give me two curves, E1 and E2, then just by looking at, for various primes L with this restriction, just look at the difference AL of E1 minus AL of E2, and if it's non-zero, then it only has finitely many primes dividing it, and that gives you a restriction on P. And then you can do this for lots of L's, take the GCD of all these differences, and you'll soon find out that whether there is a congruence or whether there isn't a congruence or not. But we don't want to do this for all pairs of curves. There are too many pairs. So we want to do something where we can somehow do a pre-computation once for each curve, and then somehow do the comparison afterwards. And one thing that makes this a bit difficult is that somehow if I store information about E1, then later on I'll get into trouble trying to compare it with E2, because E2 has a different forbidden set of primes. And there's a very simple idea that allows you to get around that, based on the fact that all of our conductors are less than or equal to 400,000, and that is simply that we only ever use primes L that are greater than 400,000. And if L is greater than 400,000, it certainly doesn't divide N1 or N2, and it won't divide P either, because I'm never going to do this for a P bigger than 100. Okay, so that's the first idea, that if you use large L, you can sort of ignore this condition here. I was very pleased when I had that idea. So, you know, as you get older, you get pleased by simpler and simpler ideas occurring to you. Okay, so we use a kind of sieving procedure together with a hash function. I hope that's not too kind of computer sciencey for this audience. So we take, so you think of a number b, and you take the first b primes bigger than 400,000, and for each b, so for all those primes, you compute, and then we take one curve at a time. This first pass through. So for each curve E, you compute AL of E for all these L's in this finite set, and then the bar on the AL of E, I don't know, this thing doesn't really work properly, does it? Okay, in that summation you see there's a bar on top of AL of E. The bar here just means reduce mod P to the range 0 to P minus 1, and then you put those into the digits of a number in base P. So that gives you, an integer, positive in the French sense, integer. So for every curve and for every p, we get this integer, and if two curves were mod p congruent, we would get the same integer. So we regard that integer value as being the hash of E at p. So any two p congruent curves have the same hash value, and we would hope that if we take b not too small, we wouldn't get any false positives. You'd get a false positive if the ALs for all the L's in the set you were using were congruent mod p, but some of the other L's weren't. Okay, and another nice thing about this is that we can parallelize it, because so if you do this for a single prime p, on the database it takes, I don't know, half an hour or something to compute all these, even without trying very hard to optimize things. I'm sure Drew over there could get it down to probably 1 minute, but it's not necessary because we only really have to do this once. And how we parallelize it? Well, most of the time taken in computing these hashes is computing the AL of E's, and you only have to do that once. And that takes most of the time, and then very quickly you can reduce mod p and put in this formula. So you can do lots of p's in parallel, and as you'll see, I'll do later on, I'll be doing all primes up to 100 together. Okay, so what do you do with these hashes? Well, whenever you find a hash, you look to see if you've seen the same hash before, and if you haven't, you make up a new kind of row in a table. So we're going to end up with a table with the rows indexed by all the different hash values, and against each hash value, we'll just list each curve that we find. Okay, so if by the end of the whole process, next to one hash value, you've only got one curve, well, that curve is definitely not p congruent to anything else. So you can throw all those away, and you're just left with the sets of curves which all have the same hash value, which you expect, if the number b there isn't too small, you expect those have a very good chance, at least, of being genuinely p congruent. And here I'm only using the traces, and so because some of these representations are reducible, I'm really, at this stage, only really checking isomorphism of the modules up to semi-simplification. Most of them are irreducible anyway. Okay, so we have some sort of post-processing to do after this, because we have to check that the congruences really do hold for all L, which we do, and we also have to do something extra in the case where the representations are reducible. I won't go into all the details of that. So this actually works very well in practice if you pick the first 40 primes, more than 400,000. When I first did it, I only picked the first 30 primes, and I found one very annoying pair of curves kept on sort of tripping me up. It was always the same pair of curves, and the reason is that if you take these two curves, so the labels are 25921, so 25921, that's the conductor, and A is the isogeny class, and what is the first curve in the class. So those two curves have exactly the same ALs for the first 35 primes of 400,000. In fact, these curves, they're twists of each other. They both have Cm by square root minus 7, so half the traces are 0 anyway, and the ones that aren't 0 just happen to be quadratic residues modulo whatever the twist is. And so when I chose 30 or even 35, this pair always was the only false clash I ever found. So eventually I turned up B to 40, and then I get no false clashes at all. 36 would be enough.
And then this interval was just like accidental. If you had started at 500,000.
Yeah, I probably should have started at 500,000 because, don't tell anyone, but I have actually started computing elliptic curves of conductor 400,001 upwards. But don't tell anyone, because I promised people that I never would, because I'd done it enough. I spent my entire life computing elliptic curves, and I really should do something else for a change. Anyway, yeah. I'd have to redo this entire calculation using 500,000 probably, yes. Anyway, yeah, so there's some more work to do with reducibility, which I don't really want to get into. It turns out that it's actually much easier for two reducible curves to have isomorphic representations after semi-simplification than to actually have genuinely isomorphic representations. But the nature of the further tests we carry out, I won't do. Oh yes, the other thing we do have to do is, I haven't proved p-congruence here. I've only proved that the ALs are congruent for this particular set of 40 primes. And so in order to prove that they really are congruent, then we use a criterion of Krauss, which is based on the Stern bound, to show that it's enough to check, after we find these congruences, it's enough to check a rather large list of primes L up to some rather large number, and I actually did that for all of these. So they all were genuinely congruent. Okay, so at the moment I'm not telling you which primes I did this for, except to say that I did this for all primes up to 100. So here's the results we get. So I put in p equals 5, although we're mainly interested in for the primes that are greater than or equal to 7. Because for 2, 3, and 5, there's a certain curve has genus 0, which I'll show you in a minute, which means that for every curve there are infinitely many other congruent curves, even infinitely many different J invariants and so on. So mod 5 congruences, and let alone mod 2 and 3, are just too common to be interesting. They're in fact over 100,000. So when I say sets here, this is sets produced by the hashing operation. So these are sets of isogeny classes with the property that any curve in any one of those isogeny classes is mod p congruent to every other curve. So there are 102, and this is the number of sets which have size greater than 1. And in fact, the maximum set hit size here was 18. And for the reducible cases, we've got sets of 430 different isogeny classes, all have the same mod 5 representation, up to semi-simplification. It's not so surprising. The thing is just determined by a couple of characters with values in F5 star. Right, so let's move on to p equals 7. So you see, 7 is a sort of the sweet spot. After 7, things start to get rare, and before 7, they're just so common they're not interesting. But 7 is sort of, they're kind of not so rare and not so common either. We have 20,138 sets of size 2 or more, of which most of them, just under 20,000, are irreducible, and these sets have size at most 5. The reducible ones, there are 255 sets, and some of them are quite big, 76. But this is only up to semi-simplification. I'll refine it on the next slide. No, not on the next slide. I've refined it down here already. So for p equals 7. So what happens? So why is the 337 bigger than 255 when I've thrown some away? Well, what's happening is that within this set of this collection of 255 sets of size up to 76, for each of those sets, we then further refine them into subsets where the congruence is the isomorphism between the modules is not just up to semi-simplification, but they're actually isomorphic. So each one of those up to 76 sets gets subdivided further. That puts the number from 255, makes it larger, and then we throw away the sets of size 1 again, and that gives you the 337. And after doing that process, none of the sets is bigger than 4. So genuinely, isomorphic mod p representations for p equals 7, we never find more than 5 isogeny classes with these mod 7 congruences. Right, so for p equals 11, there are still quite a few. They're all irreducible, and they're always just pairs, no bigger sets. Similarly, for 13, we go down to only 150 pairs, and for 17, there are only 8 pairs. And even, as I think I mentioned on an earlier slide, for 17, the 8 pairs, that's a bit of a cheat. There's really only 1 pair. The others are all quadratic twists. We'll talk about twists a bit more later, but if you take any pair of p-congruent curves and you make the same quadratic twist on both of them, you get another pair of mod p-congruent curves, even with the same symplectic type. So I could be counting this whole thing up to twist. That's a bit hard to do. I'll say a bit more about that later. Okay, so those are the congruences you find, and for 19 up to 97, you find nothing. I think until I did this, I'd done 19 and 23, but I hadn't systematically gone all the way up there. But I did it using this parallelization that I spoke of earlier. Okay? So far I haven't said anything about whether these congruences are symplectic or not. So now let's go on to do that. So when we started this project, Nuno Freitas had his great long paper, it's over 100 pages, which I gather is now to appear, with a whole lot of different local criteria for determining whether a given congruence is symplectic or antisymplectic. So in their work, they assume that E1P and E2P are congruent, and they give various criteria, which I'm not going to explain. There are lots of them, and some of them are simple, some of them are complicated, saying that, you know, if this test passes, it's symplectic, or if this test passes, then it's antisymplectic. And he came to me because he said, I'd like to know how many, how good their tests are at actually distinguishing these congruences on an actual database of real curves, because they knew that the local criteria did not apply to every congruence. But we did actually come up with some examples of curves where none of their criteria work, although they actually work really well because they apply to all the congruences we found in the database. We had to go way beyond the database to find cases where their criteria don't work. So on the one hand, all of these congruences that I found by going through the database, I gave all these pairs of curves to Nuno, who came back and told me whether they were all symplectic or not. And in the case of p equals 7, I did an entirely independent calculation based on modular curves, which I'll now go on to tell you about, which also decided whether they were symplectic or not, and happily the results agreed. That was only for p equals 7 that we have these two different methods. So yes, okay, there are lots of these tests. Some involve primes of bad reduction, some involve primes of good reduction, some of them are fast, so you try those first, some of them are slower. Nuno has an implementation of all of this in Magma. He hadn't implemented them all before we started. I kept on giving him more and more pairs of congruent curves, and he had to keep on implementing more and more and more of the criteria. Until by the end he'd implemented every single one of them, and they were all used. But he had a 100% success rate, which was nice. Okay, some of the global methods I'll mention towards the end of my talk are able to decide on the symplectic character of congruences when none of these local tests work. Right, so as I said, for p equals 7, I used a different method, which meant that in a sense we didn't need the local criteria, but we did need it for all other primes. And so this is based on modular curves, so I'll explain that briefly. So if you fix a prime p, then we have a modular curve x of p. The first speaker this morning also mentioned modular curves, so I know that's allowed to do. So x of p is a modular curve which, roughly speaking, parameterizes curves with a level p structure. So it really gives it parameterizes triples consisting of an elliptic curve and a basis for the p torsion. Right. There are subtleties in there which I won't go into. Okay, so these curves are well known. For p up to 5, they have genus 0, and they have infinitely many points over any field. For x of 7 has genus 3, and the usual model taken for that is the Klein-Quartic. It's a plane quartic curve. Next prime, 11, the genus is already 26. So using these things in practice is not going to be that easy, but for p equals 7, it's very useful. So it's not the curves x of p we'll need directly, we actually need twists of those. So if you fix, as well as p, if you fix an elliptic curve E, and let's be concrete, let's say fix an elliptic curve E over Q, then there's a certain twist of the curve x of p called x sub E of p. I'll call it x sub E plus because this is to do with symplectic congruences, and we'll have an xe minus later. So it's a twist of p in the sense that they're isomorphic over Q bar. So it's again a curve of the same genus, and the non-cuspidal points on that, each point on that corresponds to a p-congruent curve. So strictly speaking, the different rational points on x e plus of p correspond to actual pairs of another curve and a symplectic isomorphism up to scaling. If you kind of if you could get your hands on a nice explicit model for this curve xe plus of p, you might be able to find rational points on it and hence find congruent curves. We're going to apply that in the other direction because we've already got a congruent curve and we want to see does it come from xe plus of p. So that's for symplectic congruences. There is another twist called xe minus of p, which does the same thing for antisymplectic congruences. Another twist that has the same genus. Okay, so for p equals 7, Krauss and Halberstadt back in 2003 gave an explicit model for this. It's really explicit. If you tell me that the elliptic curve E is y squared equals x cubed plus ax plus b, so you have those two numbers a and b, you just their formula for xe plus of 7 is just a ternary quartic in x, y, and z, and each coefficient is a polynomial in a and b. You just plug them in, you get the quartic. And of course, that by itself isn't good enough. For each point on that, you need to know, well, what is the congruent curve? And so even to know it's J invariant, you have the map from xe plus of 7 down to the J line. That's a map of degree 168. So 168 is there because that's the order of PSL2 7. In general, it would be the order of PSL2P. So that just gives you the J invariant of the curve, but we're interested in elliptic curves, not just up to twist. So you need formulas to tell you what the actual coefficients, the actual invariants of the congruent curve E prime are. Krauss and Halberstadt's paper gives slightly incomplete formulas. They're valid away from a small finite set, but when you go through 2 million examples, you hit the exceptions pretty soon. So I needed to fill in those gaps. There's a model for xe minus of 7 in a paper of Poon and Stoll called twists of x of 7. What? I beg his pardon. Don't tell him, I'll change them later. Right? I only remember to put your name in yesterday. I said I only remember to put your name in yesterday. Anyway, more formulas for xe plus or minus 7, giving you the complete formulas for the invariance of the congruent curve were given by Tom Fisher, who goes through absolutely everything in complete detail, and for both the xe plus and the xe minus of 7, and he does it for the genus 26 curve. I haven't yet quite had the energy to implement all the formulas for xe plus or minus of 11, but I will one day. But I have done for xe plus or minus of 7. So this is how we apply them. So this is the algorithm. So this algorithm actually works over any field. Maybe exclude characteristics 2, 3, and 7. So let's say characteristic 0. So you give me two elliptic curves E and E prime, and I'm going to tell you whether they're symplectically congruent or antisymplectically congruent. So this is what I do. I compute the J invariant of the second curve, but I compute both of these twists of the modular curve attached to E, xe plus of 7 and xe minus of 7. And then the next 3 steps I do once for xe plus and once for xe minus. So we have this explicit rational map, J, and so we take J of E dash to be in the codomain, and we pull it back. So a priori, you might get 168 pre-images. You never get so many. If you get no pre-images defined over K, then the curves definitely are not symplectically congruent. If you get one or more, then you have to work a little bit harder, because then you found that E is congruent to a curve with the same J invariant as E prime, but not necessarily to E prime itself. So then that's where you use these supplementary formulas. So for every points you found in the pre-image, so these are all the points whose J invariant is J of E prime, you actually find a model for the associated curve, so I'll call that E double prime, and then you have to check whether any of the E double primes you've got is isomorphic to E prime. And if so, you've got a symplectic congruence, and otherwise you haven't, and then you do the same thing for antisymplectic. So here we don't even need to assume that they are congruent at all to start with. I carried this out for all of the congruences, all of the pairs of congruent curves we found for p equals 7, and as I said, I came to a conclusion as to whether they were congruent or not, and it agreed with what Nuno Freitas had computed using his local criteria. Right, so I haven't done it for 11 yet. Right, so what are the results? How many of these congruences are symplectic and how many are antisymplectic? I got slightly tired of typing in long numbers when I was preparing the talk, so I probably haven't told you everything. You may remember we had 19,883 non-trivial sets of isogeny classes with irreducible mod 7 representations which are mutually isomorphic. Each of those isogeny classes might have various isogenies, but we know how to test whether they induce symplectic or antisymplectic congruences, depending on whether the degree is a quadratic residue mod 7. And what happens is that in about 2/3 of the cases, all of the isomorphisms are symplectic, and in about 1/3 of the cases, you get both antisymplectic and symplectic. So in that second case, you divide all the curves in all those isogeny classes into 2 subsets, so that within each subset, the congruences are all symplectic, but between the 2 subsets is antisymplectic. And in the 12,000 first cases, the second set is empty. So that's the result of that. That's for the irreducible ones. I don't think I wrote down the numbers for the reducible. There are far fewer reducible. Reducible means that there is a 7 isogeny. And you have to go through some business of replacing one of the curves with a 7 isogenous curve sometimes. It's a bit of a mess to explain, but I decided to leave that out. Okay. Anyway, the upshot was, as I think I said 2 or 3 times already, that the local criteria certainly agree with this method, and they were always sufficient to decide on the congruence. Okay, for the primes greater than 7, so that's just 11, 13, and 17, we only have the local criteria to work with, and here's the result. This is the number of congruent pairs that we saw before, and this is how many are symplectic, how many are antisymplectic. For 17, they're all antisymplectic. Well, there's only one up to twist. I don't think it's very easy to say from those figures whether symplectic is beating antisymplectic or not. Yeah.
So, did you find any particular modular curve with lots of points?
We weren't looking at that particularly. In Krauss and Halberstadt's paper on XE of 7, they do. They find for some curves that there are many, I can't remember how many, but there are some curves which are congruent to many other curves. But I wasn't actually looking for that specifically. Drew.
Can you get a heuristic for the ratio of symplectic and antisymplectic by counting, looking at the automorphism group for PSL2s?
I haven't tried to do that. The thing is, these numbers will include quadratic twists, which really should be eliminated. It's not so hard here because they're only pairs. So, you twist a pair and you get a new pair, but it might be that one of the conductors is now outside the range and then you won't see that pair again. So it's a bit artificial. And when we have the larger sets, like we had sets of mod 7, for p equals 7, we had sets of 5 mutually congruent isogeny classes, but then if you do a quadratic twist, that set of 5 might go down to a set of 4 because one of them is outside the range. And so I wasn't quite clear how to do that. What I did do is just count all the individual J invariants. So that might be, it's not quite what you were asking, but yeah, okay. No, I haven't tried to do that. I'd be interested in talking more about that more with you. Okay. So I mentioned our theorem about the Frey-Mazur conjecture, so where we proved that there were no congruences modulo any prime greater than 100. And 100 isn't a round number. 100 is actually the number that works here, as I was able to explain. So first of all, for curves, we divide this into comparing curves of the same conductor, curves of different conductors. For curves of the same conductor, we really do just look at all pairs of curves of the same conductor up to isogeny, and we just look. We do the operation that I mentioned earlier. We just take the GCD of this difference of traces for putting in more and more L's until the GCD goes down below 19, and then we stop. So there are no congruences between curves of the same conductor. For curves of different conductors, then Nuno came up with this lemma based on some results of Krauss again. It says the following, that if you have a mod P congruence where P is at least 5, and you have different conductors, then one way around or the other, you can order the conductors in such a way that, so let's say for one of the curves, let's say the curve I, there is a prime of multiplicative reduction, so prime dividing the conductor exactly once, such that if you look at the exponent of the minimal discriminant at that prime, it's divisible by P. So all we have to do is we go through all of the conductors up to 400,000, take all the primes that divide that conductor once, look at all the elliptic curves of that conductor, which have then multiplicative reduction, and look at all the exponents we see. And just collect all the exponents we ever see. And if you do that, you find you get exponent 97. You do not get any exponents greater than 100. In fact, you get every single exponent up to 97 except 89. So there's a fact about the number 89 that you didn't know when you woke up this morning, that, if you look at all of the factorization of all the minimal discriminants of all the elliptic curves in the database at multiplicative primes, well, at any prime, in fact, you'll never find an 89th power. Anyway, so that proves that that doing all primes up to 100 was rather a happy choice, because it's exactly what you need. Okay. In my remaining few minutes, I'll tell you some of the things we found out about twists, quadratic, and I probably won't have time for the quartic and sextic ones. So here, the fact I mentioned already is that if you take a congruence and you apply the same quadratic twist on both sides, you get another congruence, and it's the same symplectic type. Okay? So I could have just tried to show everything up to twist. As I said already, that's quite hard to do, but you can count the J invariants, so these are the numbers. How many different J invariants of elliptic curves with a mod 7 congruence did we find? About 10,000, and a much smaller number with the reducible ones. And by comparison, there are over 1 million different J invariants, or in this 2.5 million curves, only 1 million different J invariants. So it's about 1%. And those are the figures for the other 3 primes. For p equals 17, I think I've given you that example already. So let's move on. These are the two J invariants of the 2 mod 17 congruents, and that's an antisymplectic congruence. Okay. What about other things between twists? Well, we found some phenomenon actually while we were looking for examples where the local criteria didn't apply. And here's something that happens whenever the image is, as if you focus on the middle of these 3, it's whenever the image of the mod P representation, so some subgroup of GL2 of P, if it's contained in the normalizer of a Cartan subgroup but not contained in the Cartan subgroup itself. So if that happens, then in particular the projective image is dihedral. It's not quite if and only if, because there are some other cases. When this happens, you can always construct a quadratic twist between the mod P representations. And I'll very briefly show you how that works. But it actually works both ways as well, that if you have a congruence between quadratic twist and you apply just a few mild conditions on top, then in fact the image is contained in the normalizer of a Cartan. So these two, with some mild conditions that ensure that the image isn't too small, these last two are equivalent. So this is how it works. So your image is contained in this Cartan subgroup normalizer, and so it has a subgroup of index 2, which is the intersection of the Cartan. And all the matrices in the normalizer of a Cartan that not in the Cartan itself all have trace 0. So here it's 0 mod P because it's a mod P representation. Okay, so if you twist in the right way, doing a quadratic twist flips the sign of half the traces. So if you make the right quadratic twist, you're flipping the sign on all the traces that were 0 anyway, so you're not changing the traces. So as long as it's irreducible, you get the same representation. That's how that works, and a very similar argument gets seen in the other direction. So in this way, you're able to not only find congruences, but actually in this situation, you can also determine whether they're symplectic or not. So we have a nice theorem about this, which is I'm very sort of proud of the proof of this. It's one of these things where the first proof took several pages and horrible calculations, and now it's really nice and succinct and. I'm happy with it. So here's the result. So if you have one of these situations where you have a P congruence between 2 quadratic twists, E and ED, and the image is contained in the normalizer of a Cartan subgroup, but not in the Cartan itself. And so the Cartan subgroup is either split or non-split, and P is either plus or minus 1 mod 4. And if you tell me those 2 pieces of information, I'll tell you whether it's symplectic. It's symplectic if it's split and 1 mod 4, or non-split and 3 mod 4, and otherwise it's antisymplectic. And we see examples of that. Usually when you have this Cartan normalizer situation, that's true for a unique Cartan subgroup. But when the image is quite small, not so small that it's the whole thing degenerates, but when it's quite small, it can happen in more than one way. So this is quite fun. If the image is C2 cross C2, then there are two ways of seeing that as a group of order 4 with a subgroup of index 2. And so you get 3 different quadratic twists, which are congruent in this case. So if you apply this in the situation where I had my map from, say, xe plus of 7 down to the j line, in this case, the j of e prime will have 3 pre-images, or maybe 4, counting the base curve. So one way in which I came across these results is asking the question, how many pre-images can you have, at least over Q? Anyway, so here's what happens. So you have these 3 different subgroups of index 2, and sometimes they're all three congruences are symplectic, and sometimes one is symplectic and the other 2 are antisymplectic. That's the only thing that can happen. The first case can only happen if K contains this is the quadratic subfield of the p-cyclotomic field. It's K adjoin, if K contains the square root of plus or minus P, whichever is 1 mod 4. In that case, then all 3 are symplectic, and in the other case, one is symplectic, and the symplectic one is the one which is a twist by square root of this P star, specifically, nothing else. I think I have an example of that, and the other 2 are antisymplectic. So here's an example. So the conductor is 2 times 3 cubed times 11 squared. So it's certainly plausible from this that you take a twist by -3 and -11, and you might get the same conductor, and in fact you do. And you get a symplectic congruence to this one. And notice this is P equals 3. Yeah, 3 congruent. So if P equals 3, then 3 star is -3. So you get a symplectic congruence with this -3 twist, but you also get antisymplectic congruences to these other 2 curves. And these can be verified by the local criteria, which we did. And OK, I've got one brief thing to say about quartic twists and one brief thing to say about sextic twists. Very brief. Very brief, very brief. 1 slide each. And OK, if you look for quartic twists, then you find that there's nothing interesting at all. The only time you ever get isomorphism between 2 curves, so for quartic twists, you have to have J invariant 1728. The only congruences you ever get are between the curve with this coefficient A and the curve with this coefficient -4A, and that's boring because they're 2 isogenous, so it's symplectic according, or not according to whether 2 mod 8, P mod 8. So there's nothing interesting there. And it's even less interesting if -1's a square, because then they're even isomorphic. For sextic twists, we have just one strange thing, so I really wanted to get to this. Here, the result, we've only done it over Q and for P equals 7, but this is what happens. You always get a kind of a boring twist with an isogenous curve. So here now the parameter is in x cubed plus b. It's the b that we're twisting. So if you place b minus 27b, you get a 3 isogenous curve. 3 is a quadratic non-residue mod 7, so that's antisymplectic. That's no surprise, but this is the funny one. This is one that we found by observation, and then I managed to actually prove it always works. If you take the curve x cubed plus b and the curve x cubed minus 28 over b, they always have symplectically mod 7 congruent with each other. And why? Well, you just work it out and it happens. I have no idea whether there's a generalization of this for larger p. I hope there might be, but we haven't done it yet. And so I'll stop there. Thank you.
So there's still time for perhaps short comments or questions. Well,
yes.
One comment. If I'm loud enough, then I might just repeat it.
I can hear you, but... Yeah.
Okay, so one thing that might be relevant is to look at diagonal modular surfaces. So that's basically taking this twisted modular curve fibered over the J line. And the geometric invariance of those curves have actually been determined by Kani and Shunts.
Yes.
So for instance, for 7 and symplectic, you get a rational surface.
Yes, sometimes you get a rational surface.
For antisymplectic, it's not. It's a K3. So that would already explain why he gets way more symplectic mod 7 congruences than antisymplectic.
I think it's by looking at the geometry of those surfaces that people reach the conclusion that probably there wouldn't be anything for greater than 23. So that's looking at the surfaces rather than just the curves. So you get a surface, I guess, when you let E1 and E2 both vary instead of fixing E1, E. Yeah. Yeah. Okay.
They go general type way before that.
Yeah. Yeah. Yes. Yes. Okay.
Okay. Any more questions or comments? So I think we may thank John again. Okay.